Tonight's speaker is Professor Prof Abbey, who's Director of Research at the School of Molecular Sciences at La Trobe University. And he's from the UK, originally from London, and he did a PhD in chemistry and then did a master's in, and that PhD was at Cambridge University, and then he did a master's in physics at UCL, University College London, I believe, and then a master's in engineering at Oxford University. And there's a whole bunch of other things, he's degrees and things he's done as well. So, you know, clearly he's not very good at making up his mind, but he's an expert in everything. And I'm really pleased and looking forward to this talk, because this to me looks like an incredible breakthrough in the ability to analyze tissues. And maybe one day this will become the standard way that pathologists will look at all sorts of tissues. Now, during the talk, if people have questions, they should type their questions into the Zoom chat function, and I'll be monitoring that. And if there's something that's particularly immediate, then I might interrupt and ask, pass that question on to Brian. But otherwise, we'll put questions to Brian at the end of the talk. So as I say, Brian is a group leader and research director at the La Trobe Institute for Molecular Sciences. He trained as a physicist. He has embedded a highly interdisciplinary approach in his research group in order to deliver new technologies of benefit to health and well-being. So maybe his next degrees will be in medicine. So it's great. I'm looking forward to hearing from you. Take it away, Brian.
Great. Thank you very much, David. I think medicine may be a bridge too far for me at my age now, but I certainly have learned a lot from from being within LIMS. I just wanted to say a big welcome to everyone. Thank you for joining this evening, and a very good evening to you all. And a huge thank you to David and the Australian and New Zealand Association for the Advancement of Science for this opportunity to talk today. As David said, my name is Brian, and I run a group over here in LIMS. First, some disclaimers. So some of the technology I describe in this talk, we are in the process of commercializing. So by the letter of the law, I don't have any financial conflicts at present, but it's something you should be aware of. And second disclaimer, I am a physicist, engineer, and chemist by background. And although I've been working furiously with pathologists and experts in cancer research over the past 5 years, I'm still a novice, I would say, in the cancer area, although some of the knowledge has rubbed off. So the topic of my talk today really came about as a result of a strong desire I had, and I'll kind of describe the particular, I guess, breakthrough moment in this talk, to really try to take an idea through from fundamental concept right through to product, I guess, if you want to put it in commercial terms. So something that would be of genuine use to society. And this invention really came about because of the embedded, highly interdisciplinary nature of LIMS. I was having a good chat to David earlier about the origin of LIMS, some of which I didn't know about. But it's a great place to work, because you essentially have physicists, chemists, biologists rubbing shoulders and discussing ideas, and that's really how this came about. So the key thing or key invention I wanted to describe today is really this brightly colored slide here, and this is what we refer to as a metamaterial, meaning a material that my lab has artificially engineered to take on properties that you don't normally find in nature, naturally occurring. And across the entire surface of this slide, at a scale around about 1,000 times smaller than the width of a human hair, are millions and millions of tiny nanostructures. And given the area of this slide is about 75 by 25 millimeters, which is the standard, slide size, packed into that area over 1 billion perfectly formed nanostructures, which act in concert to produce these colors actually that you see in the photograph. So why is it that I'm so interested in these materials, and what can they do? Well, this image will be familiar to many in the audience. If you've ever looked at cells, unstained cells under the microscope, for example, if you've just taken a Q-tip and taken a cheap swab and then transferred those epithelial cells to a microscope slide, and then tried looking under the microscope, you'll note that the image that you get doesn't look particularly exciting. In fact, sometimes you're lucky to see anything at all, because cells are generally pretty transparent and don't really have a strong natural color when you're using just a bog standard optical microscope. So these kind of images that you see on the slide at the moment are typical of what you see when you don't treat your cells with anything to enhance the contrast. Now, if we take that same tissue sample and we place it on one of these metamaterials that I showed on the previous slide, this is the image that's generated, right? It's quite a difference. Hopefully you'll notice. So these colors that you see are basically they're the result of interactions between electrons that are free to move within the layers of this metamaterial and the section of the tissue which is close to or touching the slide surface. So those interactions generate these colors that you see, and I'll explain how that is during this talk. Now, for shorthand, for simplicity, I'll refer to this type of metamaterial that we've been using for tissue imaging histology as the NanoMslide. That's our kind of trade name, I guess, for this particular metamaterial. But really, it falls into this large class of nanostructured materials that I'm going to be talking about today. So why do you what is it about the sample that is driving these color changes? Well, there's actually a variety of factors at play, and this is not something new to this research. This has been well researched over a number of years. People have used various optical techniques to and correlative techniques to characterize these factors. But what I should emphasize is that the optical properties of cells, and particularly, I guess, the differences between cancer versus normal cells have been studied in the literature, and these are some of the key factors driving those optical differences. So first of all, you have nanoscale changes in the morphology of the cell, which can be below the resolution limit of the optical microscope. Variations in the structure and composition of the cell membrane, the specific distribution of protein inside the cell we found to be really important in generating these colors that you see, and also the cell polarity, so asymmetries, I guess, in the cellular structure. And the fact is that these differences are specific to the type of system that you're looking at and the type of sample being investigated. But it's generally accepted that these optical properties of the cell actually provide you with a window not only into the structural morphology of the cell, but also give you an idea a little bit about what's going on inside the cell from the chemical perspective as well. So these colors that you see in these images aren't just false colors generated to put there to generate contrast. They're actually providing a window into what the cell is made up of, and I'll talk again about that during this talk. Now, of course, researchers, doctors, pathologists, experts whose daily job it is to examine tissues and study the structure of cells all the time are able to do this routinely, and the way that they do this is that they use dyes typically to stain the tissue, and The most common that I'm sure will be familiar to many people listening in today is known as hematoxylin and eosin, or H&E for short. And these stains have been around for at least a century to enable the study of the morphology of cells and tissues. Eosin is typically a pinkish color, and to a varying degree stains the cytoplasm, the solution inside the cell, and the extracellular matrix which supports the cell. And for most of the tissue, in most tissues, the nuclear region of the cell is typically stained blue. The process of H&E staining is really well established, and although it involves multiple steps, it's extremely straightforward. And I think typically with automation, you can complete this process in a matter of minutes. And because it goes well, because it works well, it hasn't really had any fundamental changes for the last 100 years, because it works, right? And so typically you'll generate an image like this with an H&E stain, which gives you great morphology. Now, using the NanoMslide is quite a different approach. What happens prior to the sample going on the slide is identical. Nothing changes. And then anyone who's worked with pathologists knows that they really don't like change unless they have to. So everything prior to the sample going on the slide is the same, but you remove all of the chemistry, the subsequent chemistry that you have to do. Basically, the slide itself provides the contrast. So, aside from the fact you're saving yourself a couple of minutes or some time with the staining, or avoiding the need to use chemicals, what are the advantages that might come with using this type of technology? Well, it basically comes down to the fact that with the NanoMslide, not only do you have that morphology information, but you also, as I said, have this color contrast. And when you're adding a dye or a stain, you're adding color to the tissue, which is external to the sample. But with the NanoMslide, the colors that you see don't come from the dye or the stain. They're actually generated by the properties of the tissue itself. Now, it's true, you can modify those colors by playing about with the pattern of the metamaterial, but the colors that you see are related to the local chemistry of the sample. Hence, when we're examining tissues, say, containing cancer cells, the color of those cells are not the color of the slide, but really it's the color of the cancer, hence the catchy title, I guess, of the talk. Now, I should stress not to alarm people that, most of the time a trained pathologist having good morphology from H&E is perfectly sufficient for diagnosis. But there are cases, and there is a clinical need for new technologies where having the morphology information alone may not be enough. So these kind of niche cases where there is a significant need to try to develop better solutions, and this is coming from the pathologists themselves and their needs to drive better patient outcomes. So obvious question is, where are all these colors coming from? Now, I realize this is a leap going from a slide to a cup, but hopefully you'll see the chain of logic by the end of this slide. So to understand how these slides generate these colors, you have to dig a little bit deeper into the history of metamaterials. And shown here is one of the classic early examples of the manipulation of light by nanoparticles. And this is known as Lycurgus cup, and it's been around for 1600 years. So yes, in addition to giving us aqueducts and paved roads, the Romans were also early pioneers of nanotechnology, which may know have known about. And I guess the key feature of this cup is that, depending on whether the light source is external to the cup, so reflecting off the surface, or whether the light source is coming from inside the cup, the color is completely different. So you get green in reflection, and then it turns to this red color if you have the light transmitted through the cup. And the reason for that color difference is because the glass that the cup is made from contains nanoparticles. And those nanoparticles are smaller than the wavelength of the light, and they interact with the light in a particular way, which I'll describe. And in fact, the electron microscopy has been used to measure the nanoparticles inside the Lycurgus cup to an average size of around 70 nanometers, which again is about 1,000 times smaller than the human hair. Now, 1600, over 1,000 years later, we're producing in my lab, I guess, tailored versions of this Lycurgus cup using nanofabrication. This is a modern example. And in this case, instead of the nanoparticles or nano features being randomly distributed, we place them exactly where we want them in the surface of the material. And because we can precisely, to the nanometer scale, locate these features, we can play and control and manipulate light pretty much how we'd like. And you can even play with the, and that's how we generate these different colors. It's by playing with the spacings of these nanoscale features. In this case, these are nano holes. And you can even change the polarization of the instant light and start generating different colors that way. Other uses of metamaterials include the creation of exotic materials which have refractive indices. If you recall, the refractive index is the number which determines how much light bends towards the surface normal when it passes from one material to another. So you can create through metamaterials materials with negative refractive indices, so you actually get a reflection type effect where the properties of the material are completely distinct from standard materials. And this bizarre behavior in which light is bent the wrong way can be actually exploited to create lenses which achieve super resolution optical imaging. So there's a huge range of applications for these types of metamaterials. Another example, in this slightly sinister looking figure you see on this slide, this illustrates another really famous application of metamaterials, which is for cloaking. So cloaking objects is possible using metamaterials because they can manipulate the trajectory of light to actually bend light smoothly around objects. And so when you're looking at an object cloaked in a metamaterial, you can see the features behind it because the light is continuously bent around it. And although we're not quite at the stage of the Harry Potter-like invisibility cloaks, this is not just science fiction. These materials have been developed initially at microwave wavelengths where they're easier to fabricate, but then going to ever shorter wavelengths. And there's some famous papers by Pendry and Schurig published in Science back in 2006, in which they were able to generate a metamaterial which effectively cloaked a cylinder so that you could see around it or see around it with the microwaves. So the idea is then, if you can reproduce this optically, then you've got your invisibility cloak, which I guess would be something we would all want to get hold of. But the final odd phenomenon with metamaterials I'd like to talk about, which kind of sets me up to explain how we're generating all these fantastic colors that you saw earlier, is this phenomenon known as extraordinary optical transmission. And this was an effect that was reported experimentally in Nature back in 1998 by a group led by Ebbison. And simply put, extraordinary optical transmission describes an effect whereby if you have an array of these nanoholes in a metallic film, and you work out, you can simply calculate how much light is falling on one of these holes. And from that calculation, you can work out how much you should measure on the other side, right? It should be fairly simple. If you've got an aperture, a certain amount of light falling on it, you should be able to calculate based on the area how much you expect to get through on the other side. However, when Ebbison made these measurements for these nanoholes, what he found was that he was getting a lot more light through the hole than he actually expected. And in fact, if you look at some of the wavelengths that he measured, you've got up to 10 times more light coming through than you might expect based on the size of the hole. And, you know, I can tell you one thing, and I guess this is true for all scientists: physicists just can't stand an unsolved problem. Right? You know, why should this be the case that you're getting more light out effectively than you'd expect? And the answer to this conundrum lies in considering the specific interaction of light with the electrons within this metallic film. So when you engineer a metamaterial like the one I showed in the previous slide, which is composed of all these tiny holes in a continuous metallic structure, you can satisfy a condition when you're using white light whereby some of the energy of the light goes into coupling to those free electrons. And so that coupling between the light and the electrons causes the electrons to, because they're unbound, they're free to move in the middle, it causes them to oscillate periodically back and forth. And so this periodic oscillation of the electrons in a direction parallel to the interface of the metal and the air just above it is a collective effect, and they move in concert over distances which are much greater than the wavelength of the incident light. But because these metals, these electrons only oscillate with certain frequencies, they don't absorb all of the light incident upon them. They only absorb certain frequencies within that white light. So if I remove certain frequencies from my white light, what's left is a color, right? Is a colored image, because I've gone from having a white light composed of all the wavelengths to removing some of those wavelengths, and so I generate a color, and the energy that I've removed goes into creating these oscillating coherent oscillation of electrons. And the term we normally use to describe these light-driven coherent oscillation of free electrons at this metal air boundary is known as the surface plasmon. And I guess certainly biochemists and others will be familiar with surface plasmon resonance as a technique for measuring protein-protein interactions. So this is the same type of effect. So you've got these electrons oscillating in your film. Now what happens if I start creating holes in my film, if I just remove parts of the film? Then the electrons that are moving back and forth no longer have free reign to oscillate over long length scales. They're now confined, or they now have barriers in that film. And what those barriers do is they change the frequencies that the electrons can oscillate at, and therefore they change the colors of the light that are absorbed. And so when you introduce these holes into your film, you change the color that these metamaterials appear to be, because you're absorbing different wavelengths. And what I can do is, if I want to change the color, I simply move my holes or nanoparticles further apart, or move them closer together. That changes the frequency of the oscillation of electrons, and therefore I change the color of the metamaterial. The other length scale, of course, to consider is the size of the holes themselves. So these holes through the film have a surface, and so the electrons oscillate in a confined region around the surface of these holes with a different length scale. And because they're confined to this small region, we call these the oscillation of electrons, when they're confined to this small region, they're no longer surface plasmons, they're now localized surface plasmons. Just means that they're confined. So in essence, when one of the features of plasmons is that they can transport energy from point A to point B. So you imagine the electrons are absorbing light at point A, and then they will travel they oscillate a certain distance, and they might encounter a hole or a defect or something, and then they can give up that energy again as light. So at the high level, hopefully this starts to provide some explanation for how you can get more light out of a hole than you put in. It's because not all of the the energy is coming from just from the area of the aperture. It's actually coming from regions around as well. And in fact, all of these holes act like a single material. They act in concert with one another because these oscillations of the electronic structure are long range. Now, I promise there's an end to the physics. This is just to get us to the, I guess, the key point. And my final point in this slide is I guess, a crucial one. For those of you who can recall the basics of how electricity is generated, when you have moving charges, they create a field, an electromagnetic field, which is what is shown by this animation here. So this is the electromagnetic field extending out from the surface of my metamaterial into the air around it. So my moving charges create generate these electromagnetic fields which extend out from the surface of the metamaterial into the air, and that will become very important for explaining these colors that you observe when you put tissues or cells on one of these devices. So look, I know what you're probably thinking. You came here to hear about how our amazing new technology is detecting cancer cells, and instead you're getting this tedious physics lesson. But I promise you there is a point to all of this, which will become apparent in the next few slides. So let's just have a brief review of how bad a job I guess I've done of explaining this phenomenon. If we consider again, one of these metamaterials, again, this is something that we produced in my lab. I have a white light source coming in. Typically most microscopes just use a bulb, halogen bulb, or a white light source in white LED. Then if I change the distance between these holes for the reasons I described in the previous slide, different wavelengths of this white light will be absorbed, and then that results in these different colors that you see. So we can see very clearly, and this is experimental data from this section of metamaterial, that the colors that you see by eye are incredibly sensitive to the distance between these holes. So I can basically tailor the colors and play with the shape of the holes to produce whatever output I want. Now, I make this sound incredibly easy. It's not. It takes a long time to basically do this reliably. For a long time, one of the barriers or challenges we had was making really high quality devices at big scales. Right? That's one of the key things that you have to be able to do if you want to play with these kind of applications. But that's the essential physics behind this. This is how we're manipulating light to generate colors. So if that's one way you can change the color, but how else might you think I could actually alter the color that you see under the microscope from one of these metamaterials? Well, what if I were to place something inside that electric field that these oscillating electrons are generating? Now, this is experimental data on the bottom here. So this purple color is actually what you see from one of our metamaterials when it's just in air. You get this purple color out. Now, if I just take a pipette and put a drop of water on that metamaterial, this is what happens. You basically, because that water is within the electric field, it actually dampens the oscillation of the electrons. And again, as soon as you change the frequency of oscillation, you change the colors of light that are absorbed, and you generate a different color. So what you see very clearly from the experimental data, and it turns out this is incredibly sensitive to whatever is within this electric field, is that you basically have a way of detecting chemical composition within this sensing region. I should say it doesn't matter, if your sample is much bigger than this sensing region, then basically what you'll see is whatever is within the region of this electric field, and everything else is basically transparent. So you can look at really thick samples. Typically we'd be looking at samples that were of the order of about 4 microns to 8 microns thick with the pathologists. This is typically what they like to work with.
Brian, I've got a question for you.
Yep.
In the early slides, you showed round holes, but in one of the later ones, you showed cross-shaped holes. And what are the differences, and were they designed, and what other shapes have you tried?
Yeah, you've got sharp eyes, David. So when we were developing the NanoMslide, we were playing around with all of these different factors, both from a theoretical perspective and an experimental perspective. So we started off with circles, we looked at crosses, we looked at diamonds, we did a whole range of different shapes, because what we were aiming to do is basically translate what is quite a very small change inside the cell. You know, we're talking about, you know, if you measure it optically, there's a really tiny changes. The secret sauce, I guess, to this is how you translate quite small changes, quite subtle changes, into really big color differences. And that was a combination of looking at the structure of these apertures, and also playing with their shape a bit. So those crosses, they were just another type of shape that we tried in our development pathway, I guess, when we were creating metamaterials.
And are you using lithography techniques like they use in chip manufacture? Is that how you make the holes?
Yeah, exactly right. Yeah, it's the same, similar principles to just creating microchips. You know, you can now current circuit technology, I think they can get down to sub 10 nanometer feature sizes. So, you know, they're pretty accurate. The challenge we had was trying to recreate that for less than tens of millions of dollars, because those facilities are really expensive. So we had to basically piggyback on some recent developments in nanofabrication to create the same scale and quality of structures, but much more cheaply than you do with the with the chip manufacturer. But yeah, similar principles. So hopefully, I guess another point to having the different shapes is you can play with the polarization and things like that to generate different colors. But yeah, I can chat about that at the end as well. So we've spent a really long time experimenting with these metamaterials to try to maximize their sensitivity, and we wanted to do it in a way where you didn't need any kind of fancy equipment, a spectrometer or anything else. We just wanted to use a bog standard optical microscope. And so shown here just to illustrate that kind of sensitivity is one of our test samples that we use. So we have different stripes of thicknesses of carbon. Carbon is usually pretty transparent optically. And so, you know, this is a really early prototype, but hopefully you can see, you know, just comparing the same sample top and bottom, you can detect down to about 4 nanometers pretty easily. You know, we get even clearer contrast now. And the key thing here is that, you know, this contrast that you see, these colors, don't rely on any kind of diffraction effects or, you know, birefringence, which, you know, with DIC, you would typically rely on the birefringent properties of the sample to generate contrast. It's just driven by the composition of the sample itself. So I guess the take-home message from here is that through optimizing the structure and the physics of these types of devices, you can make them incredibly sensitive within you know, particular ranges that you're interested in exploring. So the idea we came up with 6 years ago was, I was busy developing molecular sensors at the time, so we were detecting the attachment of, you know, specific binding of molecules and surfaces using these types of devices. But I was really driven by wanting to develop this kind of technology into a standard glass microscope slide. You know, my background is in phase contrast microscopy. You know, people have done fantastic things with developing fancy equipment and, you know, expensive microscopes, and, you know, but the common element to all of this is the microscope slide. You know, the humble microscope slide, a few dollars or a few cents that you spend. So we wanted to modify your standard glass microscope slide in a way that it could be used for cellular imaging without the need for any chemistry. That was really the thinking 6 years ago. And we wanted to use this slide in a way that would help pathologists primarily identify different types of cells and tissues without the need or reliance on any biomarkers. And the main features then we worked to exploit were to achieve massive contrast enhancement, preserving the quality of the morphology. You know, the morphology is still critical to diagnosis, but also with an added bonus of having some access to some of that biochemical information, which can be useful. The key features of the slide are shown here. You know, you need to have it rest on something which is rigid. Glass is great for that, and chemically inert. You need the metamaterial. You need to have a really important, and it all needs to be encapsulated in the coating, because biology doesn't like metallic surfaces. So it's got to be encapsulated. And so the and we also actually had another feature, which is we don't often discuss. We had to actually make the surface, treat the surface in a way that the cells and the tissue would stick really nicely to it. You know, we developed a method that actually promoted adhesion of the tissues. So this is the basic elements of the slide. And about 5 years ago, after having developed our prototype, we felt confident enough to start approaching biologists and pathologists. And the very first sample we looked at was supplied by Jackie Orion. Yeah, exactly right, David. So Jackie was the very first person, I guess, to put her hand up and say, I want to give these slides a go. And the key thing we wanted to know is this compatible with standard histology, basically, because, you know, we didn't want anything to change about the way researchers were doing anything. And, you know, having spent, you know, a previous year testing these slides with various chemicals and test samples, we were quite confident we might see something, at least, you know, something interesting. But when Jackie prepared her tissues and put it on the slide and we took a look at it under the microscope, I know you've already seen these images, but for us, we were totally shocked. You know, this is really what you see under the microscope. So it was such a massive contrast difference. We were really blown away, and I kind of had that thought in the back of my mind. Could be really something special, you know, if we can develop this. And so this really gave me the sense that it's worth pursuing this as a project. And but we wanted to get a lot more feedback. So Jackie was fantastic. You know, she was really keen to follow up, and she's a great researcher, by the way, in neurodegenerative disease. She has a really good research program in that area. But what we did was basically we sent slides out to whoever would listen. we had people over in the UK, I think a few in the US, but mainly around Australia. And we ended up with basically getting a heap of feedback from all of these collaborators. And, you know, as the months went by, we started receiving more and more feedback, and we had so many applications, different applications. I can't possibly list them all, but, you know, just some of the main ones. For example, we had guys using this or wanting to use these slides for medicinal chemistry. They would take leaves from their plants, press them onto the surface of the slide, remove the leaf, and, you know, without doing any chemistry, then they could get these images, and they were looking at the trichomes basically as a way of assessing the health of the plant. And this could be, you know, they wanted to develop this as an in-field test. So this was, you know, given what I learned about how difficult it is to get a medical technology to market, this was very tempting to go down this route early on of medicinal chemistry. The other application we have going is cheek swabs. People were really keen to use this as an alternative to actually look at different classifications of bacteria. So just a couple of results shown here. And again, you know, it's still incredible to me that these colors exist, you know, for these different bacteria.
If you mix those two samples of E. coli and Micrococcus, would you get a mixed picture of red dots and purple dots?
Yeah, absolutely. You should. Yeah, because there's, you know, essentially mixing them up, unless they somehow stuck together in a way where you saw a projection of the two, you should see the two populations as those distinct colors. And we've done, there's a company we're working with who are really interested in this, you know, looking for basically rapid gram staining. But I was pretty surprised because, you know, a key feature is that the sample actually stick to the surface, but these bacteria seem to adhere pretty well. And then another application we worked with some of the chemists in the UK who were interested in using this as a quick way to differentiate between different polymers. So they again were one of the early people who came to us with a potential application. So we basically were furiously collecting all of this feedback, and based on what people were telling us, we basically went through this R&D cycle for a couple of years. And look, usually I have to admit, I'm normally rushed to publish at this point here in the research and design phase, because you think, you know, great idea, let someone else do something useful with it, because it's a lot of work to, you know, to take it through to a product. But with this particular invention, I was really keen from the response that I was determined to try to refine it and actually turn it into something that could be used by other groups. So what followed was, you know, just over a year of intense refinement and development. We develop a different version of the slide, then do some testing with a third party, and then identify any issues, and then develop further, and round and round. And I felt much like my friend in the middle here, you know, just going round and round in this cycle. But during this phase of development and testing, there was one group who really got our attention with their application, and this takes me to the second half of my talk, which was the cancer guys, the cancer researchers, because this was, you know, a field I had no familiarity with, but I was very fortunate to be based at LIMS. As I said, we have physicists, chemists, biochemists, and cancer researchers all under one roof. And Belinda Parker, who at the time was based in LIMS, had been trying these slides with her cancer mouse model, and she reported, you know, she phoned me up, I think a couple of days later, and she was reporting that basically the cancer cells in her mouse model were lighting up, you know, a different color to the healthy cells, and she thought that this could be really useful for trying to identify small populations of cells. You know, she was interested in trying to improve diagnosis of cancer at the very earliest stages. And so since our and this was a particular problem, and we've heard this subsequently from pathologists as well, that for these really early stage cancers, the current commercial solutions aren't really of sufficient efficacy to provide you know, confidence in the diagnosis generally. So there's I guess a dissatisfaction with the current solutions. And because these NanoMslides don't use any chemistry, there seemed to be an opportunity really to work with Belinda and her colleagues to try to develop a more reliable test for these very, very early stage cancers, and particularly breast cancer, which was the area she was working in. And look, you know, it's very hard to ignore the compelling case for wanting to improve accuracy of diagnosis with cancers. You know, a statistic which is widely known but is still quite shocking is that 1 in 8 women will be diagnosed with breast cancer during their lifetime. There's a national mammography screening program and increased awareness and better detection, which means that you're picking up more and more very early stage cancers, which is great for patient outcomes, but it creates more challenges in terms of diagnosis, because morphologically these samples are more complex. And you know, there's also a problem that abnormal growth of benign cells, you know, can be difficult to differentiate from true cancers, and so this in turn, you know, leads to errors in terms of over or under treatment, which again has a critical impact for the patient. Another statistic which, you know, is a bit, you know, is concerning, you know, there's no getting around it, is the fact that, you know, a patient often, if they do have to go through to operation, will then have to come back for a repeat surgery, you know, in almost 40% of the cases, which is really something, you know, we'd like to address. And in fact, there are technologies coming through that are helping, I think, to address this problem. There's also, I won't spend too much time on this. I guess I've got this slide because I'm very used to talking to VCs and investors, but there is a strong health economic argument around this as well. there's, as I said, the amount of or number of early stage cancers is increasing. A third-party market research report has basically shown that even though they're a relatively small proportion, so you shouldn't worry too much. Pathologists are pretty good at their job. Most cases the diagnosis is accurate, but even though they account for a relatively small proportion of cases, because they are so much more complex, they actually count for a disproportionate size of the market. And there's a paper now a few years old, which estimates that the cost of misdiagnosis for early stage breast cancer is almost $40,000 per patient per error, which is really quite significant. So given that there's a clinical need and a health economic argument, we now needed to think about how the NanoMslide could fit in a clinical setting. How could pathologists actually use this technology, given it is an extremely conservative area, and they really are reluctant to change current practice unless there's a real strong driver. So as I said, currently H&E staining, as I discussed at the beginning of the talk, is performed in every tissue as standard, every tissue section. But around 30% of the time, additional immunohistochemistry is ordered. And this is because the morphology from H&E doesn't yield a clear diagnosis. So immunohistochemistry involves selectively identifying particular proteins in cells, which may be characteristic of certain cellular events, such as proliferation, where cells divide and multiply. And because cancer cells, some of these markers rely on the fact that cancer cells have a different rate of proliferation to normal cells, and then that's how they then bind and identify the suspected cancer regions. The problem is that at the very earliest stages, it can be hard to detect the presence of these particular proteins that the biomarkers rely upon. And you may be, some pathologists have said it's like looking for a needle in a haystack sometimes when you're at the very earliest stages and the cancer cells haven't invaded out of the ductal region. So it's a challenge to identify exactly where you should look, even to diagnose. So the idea that we wanted to come up with, and this just shows all the different steps that you have to take to do immunohistochemistry. I should say as well, although rebates against immunohistochemistry, MBS rebates, for those who know about such things, are quite large, pathology labs don't make a heap of money out of these tests because of all the work involved, and it's quite a lean area. And so it's it's complex and challenging on a number of fronts, really. So the way in which NanoMslide is actually being used, or has been used at the moment, is as an alternative to immunohistochemistry. Since an image is generated basically as soon as the tissue is placed and makes contact with the slide, it means that you don't have to break the workflow to wait for these additional results to come through. And most importantly, and really this is the only real thing that pathologists care about, it has to work better than the current alternative. If you don't have a technology that works better than what can be done currently, really you won't get anywhere. So the way in which our slides have been used is actually in conjunction with H&E. H&E is the gold standard, but they're being used as a way of identifying those suspect regions, and then you have the combination of the morphology and the biochemistry, which then leads to a more definitive diagnosis. And look, I'm not able to be there in person. I would love to do an in-person demonstration with our little portable microscope slide, but I just wanted to show you one of the slides being used. And there's no delay in attaining image. You pretty much just put the sample on and scan the slide under the microscope.
Have these ones also been stained with H&E, or are these just the NanoSlide?
This is just NanoSlide. So I'll talk a little bit about the way the comparisons were set up, but yeah, we basically just had NanoSlide, H&E, and then the biomarkers on separate tissues. So the early results from Belinda's mouse model, we looked at just a small number, about 24 lesions, but she was pretty happy with the results. There seemed to be a clear differentiation between these different stages. So we then contacted a number of sites, including Olivia Newton-John Cancer Research Institute, Royal Melbourne Hospital, and New South Wales Health Pathology, to try to obtain, basically source some real world, some patient samples. And we were really relying, you know, I can't emphasize this enough, I'm not a pathologist, so we were really relying on the goodwill and motivation of the pathologists involved in this study to really, you know, manage the study and set things up for us. And they were using a retrospective patient cohort, which meant that we could compare at the high level the diagnosis, the diagnostic outcomes, so that we had some further confidence in the result. So what we did for each biopsy was the pathologist would cut 4 sections consecutively, one on the NanoMslide, one on the H&E, and then the 2 on the biomarkers.
And are these frozen sections, or are they fixed paraffin embedded?
No, these were FPPE. These were embedded, yeah, in paraffin embedded. And because they were consecutive sections, the morphology wasn't exactly the same, but you could basically overlay the images and do some direct comparison. And this is just some example images from these different methods. And although, you know, I don't know if you can see these little green dots, the resolution isn't great, but those are essentially the cancer cells under the microscope. They tend to present as this dark greenish color against the adipose tissue. So this summarizes, I guess, the pathology scoring. This was done at 2 sites, one at New South Wales Health and the other in Melbourne. The samples were randomized, and the scoring is basically done on how much within the field of view of the microscope the pathologist thinks is cancerous versus healthy. Now, this is my physicist understanding of how they score, but you know, that's how they described it to us. And they were, you know, I have to emphasize, these are small numbers of patients, you know, 24 patients in this particular study, but they were really happy with the level of differentiation they were getting between these different stages. You know, in particular, you know, usually they struggle to differentiate hyperplasia from DCIS. You know, this is a tough one. So we were getting quite nice differentiation. We originally wanted to recruit 60 patients, but when the pandemic hit, things kind of slowed down a bit, and we ended up with 24. But luckily, the statistics were just sufficient to be able to build confidence that things were working as we hoped. So, you know, you can imagine, you know, 6 years since we first came up with the idea. For reasons I can discuss at the end of this talk, it took 4 years to get all the evidence for the paper kind of together, mainly because I wanted to see it working in humans as well as in mice. You know, and I can tell you that the standards for getting clinical data or published in Nature are very tough, very tough. But look, we obviously were, you know, delighted to get the outcome, and this leads to the obvious question of what next, right? Where do we go from here? We're in the process of expanding the patient cohort. We need to prove these early results with a much larger body of patients. We're looking at trying to go to about 100 to 150 patients as the next step. And clearly, there's value in developing technologies which can generate high quality bioimaging data instantly in cases where you're actually in an in-surgery situation. And this goes to your question about frozen sections, David. So one of the early applications that we wanted to pursue was seeing whether this actually could help in a surgical setting produce a rapid, reliable, instant result for the surgeon of where tumor margins were present. The way we envisage this working is that basically you put your frozen section onto the NanoMslide, you scan in the data, you know, just take a regular microscope, take a digital image, analyze the color output, and then use those colors to form a contour around the tumor. You would then, and this is, you know, to maintain the highest standards, have a pathologist either verify the results or independently, you know, using the color contrast, outline the tumor, and then you could compare directly. So this is an application we're working on right now. And again, I think there is a real need for this kind of technology. Very briefly, we haven't published this yet, but so I'm taking a risk in presenting this to you guys. But we also have some indications that you actually get a color change in your cancer cells well before you get any noticeable change in the morphology. So these three classifications, we looked at totally healthy mice, so mice that would not go on to develop cancer. But we also looked at mice at the really earlier stages of cancer before you get any significant staining with the biomarker, for example. And it does seem that there is some level of differentiation. Again, small numbers of samples, but it's quite exciting, really, if this could actually predict which cells would go on to become cancerous. And I'll just very briefly skip through these final slides. But as I said, my background is in phase contrast imaging. So of course, I had to combine this NanoMslide technology with phase contrast, and we actually published this in Nature Photonics earlier this year. And I guess the headline grabbing message is actually the improvement in contrast was even greater than you get with regular microscopy. We had 100 times improvement in the contrast of the phase imaging. So this was a fantastic result for us. And my final, I guess, slide I wanted to highlight is that we are now really hoping that Australia is going to invest in advanced manufacturing technology. So we're able to produce, around about 1,000 slides a month at the moment. But if we get access, I guess, to these, things like roll-to-roll manufacture, where you've got kilometers long streams of metal and then you're imprinting them to the nanoscale. I would love to see this technology, in every lab, maybe even in the classroom, and used basically globally. So this leads me to really thank the team. Of course, my co-inventor Eugenio, who's the nanofabrication brains behind all of this. I kind of have the big vision, I guess, but he's really the technical genius. Belinda, who has been fantastic. She really identified this need in cancer. Sandra O'Toole, our senior pathologist, who's been running the studies and kind of designing things for us, and Natalia Alvarez and Darcel Thompson, who've been helping us commercialize, and fingers crossed we'll be able to get this technology out on the market at some point. So with that, and I guess with so many new technologies, I suspect most of us, whether we're aware of it or not, I think nanomaterials like the ones I've talked about today are going to slowly permeate medical technology and medical devices. And I really hope they will result in benefits that will improve health and well-being for us all. So with that, I'd just like to wish everyone a huge thank you for staying with me all this time and for your attention. And yeah, I wish everyone a good evening and welcome any questions. Thank you.
Right, that was absolutely fantastic, and I'm sure the questions will come through on the chat function. But I'd just like to take Chairman's privilege and just make the comment that there've been big prizes for invention of electron microscope and scanning, tunneling microscopy, and phase contrast. I think also got a Nobel Prize. So I predict this will be another one. That's where I'm nailing my colours to the wall. So there's a couple of questions. One question was about can this be used for blood cancers? If you for leukemias, if you lysed or got rid of the red blood cells, could you put down the white blood cells on the slides?
Yeah, I mean, you can. The only requirement is that the cell is close to or touches the surface of the slide. We can't guarantee, that it will work for other types of cancers, but what I can guarantee is you'll see, this high contrast colored image, and then it really depends on whether it's telling you something useful or not. So we've done some work, for example, in lung cancer, colon cancer, and it seems really promising. But I would love to try and just see if it can be used. But
it is in essence telling you a difference in the biochemistry between the tumor cell and the other cell. So.
Exactly right. And the key thing is whether those differences in the biochemistry are sufficiently large to overcome the heterogeneity in the cells, because there's always heterogeneity in biology. So you've got to, that's the key question. But one of the great things of this technology is you can actually tailor it for a particular problem. So if there's a really high impact clinical need out there, then we can actually work together to try to solve it.
There's a question from Malcolm Jenkins. Cell adhesion is important in stem cell differentiation and bioreactor substrate performance. Can this technique be used to assess tissue adhesion to a substrate?
I can tell you it's incredibly sensitive to tissue adhesion. So our sensor region extends, we can tailor it to extend up to a micron. Typically it extends about 300 nanometers. As soon as you break contact with the surface, so that we treat the surface, as I said, so the stuff sticks really well to the surface of the slide. As soon as you break contact, you'll see an instant color change.
So how critical is it to the thickness of the slice?
So if you're working with slices that are a micron or thicker, doesn't really matter.
So it's just the contact that matters, not how much is piled up on top of it.
Yeah, and unless you're working with really thin sections. So we did some work with TEM sections, and there, you will notice if there's differences in the thickness or roughness, they'll show up. But ultra microtome is pretty damn good. You can get to about 1 to 2% variation. So,
and how long do the slides keep?
Because they're sealed, they've got, it's the same as a regular slide. It's all they're encapsulated basically within this kind of glass-like material.
All right. Well, most of the comments are just saying thank you, brilliant, well done, fantastic work, fantastic talk, etc., etc. So I think that's a good note to end on. So thank you.